Whenever we have fractions, we kind of don't want fractions with surds at the bottom. Um, we kind of, it's easier to look at these fractions and say, okay, well, I don't know exactly what the square root of 2 is, 1 point something, 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 but I know these are quarters, and I don't really know what this is going to be, but I know at least it's thirds. But when I look at this, it's like three whatevers. I mean, that is okay, this one is a very bad example. Let's just do 5. Okay, there we go. Cool. So these are very tricky to work out. So in math, we usually don't want surds or these kind of radicals underneath for the denominator. So we rather want to see this. It's easier to add whenever we add, maybe when we want to add some fractions together. It's just a lot easier to work with. It looks nicer, and this is kind of good math manners, if you want to say like this. If you do a lot of calculator stuff, I guess this is fine. But for for school and everything like this, and especially for IG exams, they want fractions with actual numbers or integers as denominators. And to change something from this, obviously these are not equivalent; they're not the same. But to change something like this into this, we call it rationalizing the denominator, because this is an irrational number. We actually want to rationalize it. So how we do it is, I'm going to just do a quick, let's say, example here of if I had a half and I wanted to make an equivalent fraction of this, what I would do is I would multiply the top and bottom with the same number. So in this case, maybe 2. So 1 times 2 is 2, and 2 times 2 is 4. So what I have here is this and this, they're the same thing. Both are a half, but I kind of changed it. I multiplied it by a magic 1. So 2 over 2 is basically 1. And I made an equivalent fraction. I'm going to try and do the same thing here. So let's write down our example. I'll do some color coding. So 2 over the square root of 5. And I'm going to multiply top and bottom with 1, but I'm going to do a special one. So I'm going to do the square root of 5 over the square root of 5. And you might say, okay, well, that doesn't really look nice. But what's really nice here is when I multiply the square root of 5 times the square root of 5 will just give me 5. Okay, and then 2 times the square root of 5 is just 2. Let's do a very nice color coding here, square root of 5. So now I've rationalized this, and I know this is fifths. And if I wanted to add this or do some calculations, it's a lot easier to work with this than with that. Just a quick note, if you didn't get this part, if you want to do a little test, let's say the square root of 4 times the square root of 4 is going to be 4. But if you want to test this, what's the square root of 4? Well, that's 2. And what's the square root of 4? Well, that's 2 as well. And 2 times 2 is 4. You want to do the same with a 9. So it works with the square numbers. It's easier to work out because 3 times 3 is 9. So if I do the square root of 10 times the square root of 10, that'll just be 10. If you want to go really advanced look at indices, let's say 10, square root of 10 is 10 to the power of a half, right? And if you multiply 10 to another power of a half, what is the rule? So usually I'll have the base would stay the same, and I'll add the indices. So what's a half plus a half? That's 1. So that's kind of the technical reason for it. But yeah, let's quickly rationalize some more not equations, fractions here. So let's do the 3 one. So I have 3 over the square root of 3. And in this case, I'm going to multiply with, well, you guessed it, the square root of 3 on both sides. Well, top and bottom, not both sides. It's not an equation. Okay, and then this is going to give me 3, and this is going to be 3 and the square root of 3. But I see something special now. I see that this 3 and this 3, so what is 3 over 3? That is equal to 1, right? So they reduce to 1, and I'm left with the square root of 3. Okay, I'm going to do, let's say, one more example. Okay, let's just think of something. Let's do 10. Yeah, let's do something weird like this. 10 over 6. Now both have square roots, or both are surds. Now this is going to be, I think it's going to go long. There's a long and short way. I'll do the short way later, but let's just do the long way first. So in this case, I'm going to have to multiply with the square root of 6 tops and bottom. So at the top, I'm going to have the square root of 10 times the square root of 6. And the bottom will just be 6, right? So what I did here is I multiplied with the square root of 6 top and bottom. And this times this gives 6, and this times this gives that. Now this is going to be the same as, I'll go really long to show all the steps. It's going to be that, and then this is going to be the square root of 60 over 6. But 60 is, I should be able to simplify this. There are, if you watch the previous video, you should know how to simplify surds. And there is definitely a square number factor in here. So when we simplify surds, just to recap, I want to find a square number that's a factor. And in this case, there's a 4. So I can rewrite this as the square root of 4. Well, let's just do it the very, very long way. 4 times 15 is going to give me 60. And that's going to be over 6. And this is going to be the same as the square root of 4 times the square root of 15 over 6. I'm running out of space here. That's going to be 2 times the square root of 15 over 6. I'm going to carry on here. Very mathematically. Very nice. And the 2 over 6 is just going to be 1 over 3. So basically I'm going to end with 15 over 3. Because 2 over 6 is the same as, I didn't write the 1, but I'll do it there, 1 over 3. Okay, just take that out. And this is my answer. There is another surd rule. We'll do videos on that later, or I might have, depending on when you watch this. There is a different way of doing this. When you divide, you can actually go this route, 10 over 6, and the square root of that whole thing. So this and this is the same, just like when we multiply, we can break them up. With division, it works the same. And I can reduce this to what number can go in both? 2. So this is going to be 5 over 3, and that's the square root. It's not really a lot quicker, but basically this is the square root of 5 over the square root of 3 multiplied. Okay, so this is now not a rational number. So what I do here is I do our little trick that we've done all the time. And what do we get? The square root of 3 times the square root of 3 would just be 3. And then 3 times 5 is going to be 15 under the square root. So we see it's the same thing. Maybe this is a bit quicker, but because you're kind of simplifying first, and then you don't have to simplify here. But yeah, both work.